EnVision is an initiative by a team from VIT University, Chennai. We envision to develop a car which will be autonomous in decision making required while driving on Indian roads. We want to revolutionize the way people visualize road transport.
Let's go back for a brief history of cars and automobiles. From the beginning, automobile industry developed, and today we drive cars with numerous human assisting sensors to maximize safety and ease of driving. But still accidents happen. The stats of the number of accidents are not hidden. Most of them are caused due to drivers' mistakes in analyzing the road and in taking suitable decisions. When we talk about perfection, we need technology. So it's time for something new, automatic. It's time for driverless cars. The objectives of the first phase of this project are the midpoint detection, direction control, on-road PID detection, object or vehicle speed detection, other vehicle direction detection, and lastly the traffic signal detection. For these objectives to be catered, a generic set of database was recorded using Santro Zinc car both at day and night time. The database covered following specifications to improve the robustness of the algorithm and to make it more generic. Some of the specifications which were taken care of, like shadows, presence of other vehicles, presence of pits on road, the type of road, whether it is a well-laid road or a rubble road, the presence of headlight, the visibility of the road or lane edges. Moving on to the database, this sample of video was taken at a daytime at 3 p.m. The cases covered in this video were vehicles overtaking your own car, like the bike just overtook, pedestrian, uneven terrain, and the trees. This sample is from a video which was taken at another daytime. The red line on the hood of the car was used to provide reference. This sample shows the scenario of unmetalled roads, which is common in India. The cases covered are the shadows of the tree, unclear edges, shorter lanes, and shaking of video due to bumpy roads. The next is a sample which is from a video which was taken at night time. The cases covered by this sample are low illumination, partial lighting of roads due to focused headlights, and invisible edges at times. Moving on to the working of the algorithm. This flowchart describes how a frame undergoes multiple processing and how useful data gets extracted. The frame acquisition module acquires video in real time from a camera installed in the car. This frame is sent to two modules. One is the midpoint detection module and the other is the interframe processing module. The midpoint detection module works on the frame to generate edge and midpoint information, which is further sent to speed estimation module and control module. The interframe processing module processes two extracted frames, and the resultant interest points are provided to the speed estimation module, which along with the data from midpoint detection module provides the speed of the obstacles relative to the vehicle speed. This is the initial output of the midpoint detection module. The red marker in the middle shows the physical midpoint of the road. This is the output of the midpoint detection module on the night frames. This sample shows the virtual edge algorithm in case
one of the edges is not visible. The blue line indicates the visible edge, whereas the red line on the left is created by the virtual edge algorithm, as actual edge cannot be extracted.
This shows the output of the virtual edge algorithm at day times when the left edge is not visible. This is the path traced by the control module on the sample video taken at the original roadmap shown on the left side of the video. The black marker on the left side of the video indicates the direction in which your vehicle should move to reach the midpoint of the road. The right part of the video is tracing the original roadmap according to the algorithm or the position of the midpoint of the road.
Let's move to the speed detection module. An image is just the projection of some other plane to the plane of the camera. If the angle between the camera plane and the horizontal plane, that is the road, is known, the distance between the car and the object can be found. This algorithm is implemented after the number of objects and the position of objects are known. The difference in object pixel position gives the projected distance between the two objects, which when divided by the cosine of the angle between the plane of the camera and the plane of the road, gives the actual distance in pixels. This value, when divided by the resolution in terms of pixels per meter, gives the actual distance between the car and the object. The distance so found, if divided by the time between the two frames, gives the speed of the object.
Moving on to the inter-frame processing module, the first frame on the left side shows a red colored car closer to your vehicle, and in the next frame it overtakes you and becomes farther. The speeded up robust features are extracted from both of the 2D grayscale conversion of the RGB image frames. Feature vectors and descriptors are extracted from the intensity image in form of a M by N matrix from a previously determined surf features, and the points corresponding to the descriptors are known as valid points. The extracted features are then matched, and the most likely matching features are recorded in a 2D matrix. These are the accomplishments so far. In the second phase of the project, we will be incorporating the IR module to detect humans or animals on road and the proximity detection as well. The code will be implemented on Zinc board by Xilinx. Collision detection and warning system will be added, and the whole algorithm will be mechanized using proper control systems.
Thank you.